This is an AS Decision 1 question on Dijkstra's algorithm. A simply connected graph is a connected graph in which any two vertices are directly connected by at most one arc and no vertex is directly connected to itself. So in other words, there's no loops. Part A. Given that a simply connected graph has exactly 4 vertices, part I or part 1 of part A, write down the minimum number of arcs it can have. Now, in a simply connected graph with n vertices, the minimum number of arcs is n minus 1. So in our simply connected graph, n is 4, n minus 1 is 3. So the minimum number of arcs is going to be 3 arcs, n minus 1. Part 2 or part II, we need to write down the maximum number of arcs that this 4 vertex simply connected graph can have. Now, in a simply connected graph with n vertices, the maximum number of arcs is n over 2 times by n minus 1. Let's change that in to is. So again, n is 4 in this part, so we're going to have 4 over 2 times by 4 minus 1. So here we have 2 times by 3. So the maximum number of arcs is going to be 6. Part B, and the first part of part B, draw a simply connected graph that has exactly 4 vertices and exactly 5 arcs. So I guess the most straightforward way to do this would be just to draw my 4 vertices in a square and then draw my arcs in so that I can have exactly 4 vertices. So it means that all of the vertices need to be connected to each other. Let's have a look. So 1, 2, 3, 4 and 5. Okay, I guess there are sort of other ways of doing this, but I think they're just going to look like rotations or reflections of this connected graph here. Part 2 of part B, state with justification whether your graph is Eulerian, semi-Eulerian or neither. So just a reminder of definitions. A graph is Eulerian if all of the vertices have even degree, and a graph is semi-Eulerian if exactly 2 vertices have odd degree. So let's write down what the degree of these vertices are. So we've got over here 1, 2, 3. So we've got degree of 3 here, and then 2 is the other one at the top, and then 2 here, and then 3 here. So I can see that I've got exactly 2 vertices with odd degree, so this graph is semi-Eulerian. And the question does say with justification, so we can't just write semi-Eulerian. So we need to say semi-Eulerian, I'm having trouble pronouncing that, since exactly, and it's exactly basically what I've written down at the side, exactly 2 vertices have this odd degree. Have odd degree. Part C. By considering the orders of the vertices, explain why there is only one simply connected graph with exactly 4 vertices and exactly 5 arcs. So to help us answer this part of the question, we need to know this piece of information here, that in any undirected graph, the sum of the vertices is equal to 2 times the number of edges, and this leads to a result known as Euler's handshaking lemma, which is the number of odd vertices must be even. That includes having no even or no odd vertices. So from my simply connected graph here, I can work out the sum of the vertices, and that's just going to be 3 plus 3 plus 2 plus 2, which is 10. And this is equal to 2 times the number of edges or arcs and the number of arcs we've got here is 5. So in other words, if we have 5 arcs, the sum of the vertices must be 10. And if the sum of the vertices must be 10, because it's a undirected graph, that means that the number of odd vertices that we need to make sum up to 10 needs to be even or 0. So we're going to write down what all the different combinations are. So it could be that they're all even. And if they're all even, there's only one combination, and that is that we have one vertex with an order of 4 and the others are 2. That's the only way that we can make the sum of the vertices add up to 10. Now, it's not possible in a simply connected graph to have a vertex that's got an order of 4, because there are only other 3 vertices to connect it to. You would end up with a loop. So this one isn't possible. So not possible. And the reason for that is because we would end up with a loop. And that's not allowed. Another option is that they're all odd. That would be an even number of odd vertices, because all 4 of them would be odd. Now, what would the orders have to be? So I think the only option we've got is 3 3s and a 1. Now, this is not possible. You cannot have 3 vertices that have order 3 that connected to 3 other vertices and just have one vertex just connected to just one other vertex. So I'll show you what I mean. Let's just get rid of this text here, and we'll try and draw that out, and you'll see that it's impossible. We can't do it. So I'll draw out my 4 vertices. I want to get rid of this text here, and we'll try doing it. So 1 2 3 4. Right, so we'll give this one order 3. Okay, so this is now got order 3. We'll give this one order 3. Okay, so it's got order 3 now. The one at the top, we'll give that one order 3 as well. The last one automatically has order 3. So we cannot make one of the vertices order 1, because all 3 other vertices have to be connected to it. It's impossible. So they can't be all even. Vertices, they can't be all odd. So the last option is that we have 2 odd vertices. Now, if you're going to have 2 odd vertices and the order of each vertex needs to be less than 4, the maximum it can be is 3. The only option we've got is 2 3s, that makes 6, and then a 2, and then a 2. Now at this point we can go back to this piece of information that we had here. In any undirected graph, the sum of the vertices equals 2 times the number of edges. Well, the sum of the vertices here, if 2 of them are odd, is going to be 3 plus 3 plus 2 plus 2, which is 10. And we know that that's got to be equal to 2 times the number of edges. So 10 is equal to 2 times the number of edges, which must mean that the number of edges is 5. So number of edges has to be 5. So we'll finish off by writing down a conclusion. Anytime you do any type of question like this, or you're doing any type of proof, you want to write a conclusion at the end, which is what we're going to do. And that conclusion is just restating what's given in the question. Therefore, there is only one simply connected graph with exactly 4 vertices and exactly 5 arcs. And you can also see that this piece of information here corresponds to the simply connected graph that we drew here. 2 odd vertices and 2 vertices of order 2.